Howdy, everybody. We're here for the recap of 2015 for Advent of Code. So I think it was a fun year. I feel like I learned a lot and got some things done and improved, in that respect. Kind of prep myself for the upcoming things. I think I'm going to probably move on to 2016, keep doing this, see if I can't get better and learn more things. Definitely learned a lot of stuff. So there'll be a lot of things to talk about. Just like I wrote this little script that will show that you can kind of see on the right hand side here. So the total runtime after I did some optimizations, day 24 was a big one I needed to optimize. I able to get the whole thing running under a second. Here's all my times. The resolution isn't perfect, but it's probably close enough. A lot of these are in the microseconds type things. So anyway, we'll I think the day, or I think I should say the year was a success. I feel like I learned a lot. Hopefully you've learned a lot well. And what I plan to do for these for this video, this recap, is kind of go over some code changes that I made that I felt were like worthwhile or helped me learn something new. A lot of it came from the comments. So again, thank you very much, everybody, for your comments and your thoughts. It really gives me insight into like utilizing, Rust appropriately for like what you're doing, right? I think one of the big things is like when you pick a language that you want to do programming in, especially competitively, is like finding ways to do it idiomatically is important, but also like ways that the compiler will like be better able to help you as well, if that makes sense. So anyway, that's kind of where we're going to go. And let me bring up my notes here and we'll start talking. So I think the first one for day 3, a lot of what I did was try to make things more functional. I found that in a lot of cases, the functional solutions feel more readable because you're like reading line by line. Here's what I want to do, as long as you understand the functional aspects of it, right? So one thing that I learned was this scan function, which I actually think I've used before, but feel like I forgot more things than I've ever learned. Does that even make sense? Forgot more things than I've ever learned. Yeah, I don't know how that works. Anyway, the scan thing I think is kind of cool, right? The idea is, so when you're think about how your functional loop is iterating, right? You things are like sometimes obvious, right? Where you say like, oh, I can do a map which says take this object and transmute it into this other object and then continue that thing down the pipeline. And then sum is fairly obvious, right? Where you're saying like, okay, as the objects are coming in, like add them up, sum them together into some object that makes them summable. Fold is a common one as well, though used less often, right? But it is powerful. The idea with fold is you say, I'm going to give you some initial value, and then I'm going to give you that accumulated value in each function call and the value that's going through the pipeline, and then you do work and you update the accumulator part, and it will track that accumulator, and then the fold, when it's done, returns the accumulator. So you could implement sum using fold, right? Think about if you used fold for sum, obviously you wouldn't do this in real life, but you'd say like, oh, I'm going to start the accumulator at 0, and then for every number I get, I'm going to increment the accumulator by that number. And that's how a fold would work. Scan works similar to fold, except it returns the objects that have changed. So your goal is in the scan is to mutate the accumulator in some way, but then you return the accumulator. And this can be useful um, if you think about it, the way to think about scan, I think sometimes, is if you have a for loop where you're doing something over and over again, and you want to like spit out the results of that for loop, save it somewhere, like maybe in a hash set or a hash map. You can use scan to essentially do that stuff for you, like print out those mutated values and then use those values however you need to. So this previous code, I actually don't remember exactly what it looked like. We can go back and look, or you can go back and look at yourself. But the idea was, I think what we were doing at the time is we were looping through the values and storing them in a hash set. The updated values, storing them in a hash set, and then we could return, you know, the length of the hash set to say here's how many unique points Santa had visited, right? In our case though, because we knew in our case though, if we're using scan, sorry, hold on, let me zoom in a little bit. Because we're using scan, what we can do is just, you know, update where Santa is at each interval. So this scan is going to update Santa's position and return that value through every single time. And then obviously I add the initial point to it as well. But then I can call this unique function and get a count of the unique values. So this is a much more functional way of doing this. I get unique from itertools. So itertools is commonly used in Rust. It's pretty powerful. Obviously, it's not the standard library, so you have to decide, you know, do I want to, you know, stick to the standard library, or am I allowed to use things like itertools? But the idea here is I can say, oh, I can scan through. So I start at my initial point, and then the scan is going to update the point each step. And then with those updates, it's going to spit those out, and I can uniqueify them and then count them. And so this is the same. You can compare and contrast, but I found it feels like once you know what like scan does, what chain does, what unique does, other things like that, kind of feels cool. And you can actually do pretty cool things with it. So if you remember in part 1, you were just kind of tracking which houses Santa visited based on the arrows you got. In part 2, there was a Robo Santa, and you were alternating where you were. You can use scan for that too, right? So you say, oh, I'm going to enumerate over the characters, and then I'm going to scan all of the characters, but I'm going to keep track of 2 points. And because I'm enumerating, I'll now get my 2 different points in each call to my closure here, as well as what my enumeration is and the actual character value. And now what I can do is some funny math and say, oh, I can just alternate between using you know, this left one and this right one. I think technically it does the right one first, then the left one. Doesn't matter for the problem. But the idea is I can alternate between the moving of the Santa and the Robo Santa by just saying, hey, divide my index, or determine if I'm the first one or the second one based on my enumeration, and then I just update its next value and return it, right? So now I have all these points that are coming out, alternating between, how do I say this? My accumulator is still tracking 2 points, but I'm only spitting out the updated point for each scan. And so now I'm getting this scan is basically spitting out Santa's position, then Robo Santa's position, then Santa's position, then Robo Santa's position. And that's all I was interested in. And then I can just do the same thing as before at the ending, right? Is I keep track and I spit out Santa's, then Robo Santa's, Santa's, Robo Santa's, and between those two make a unique set of values. So anyway, this is all to say, maybe you're interested in using scan for some of your problem solving. I think a for loop is probably a known thing, right? But you may say like, oh, scan and this function chaining is maybe like more idiomatic in Rust. There's arguments for when to use one or the other. Anyway, I think it's up to you to decide that, but this was just one of the things that I had learned about when I was looking for ways to improve. And so maybe that you'll find this scan thing interesting to you as well. So give it a try, see how it works. Happy to answer any questions about it. Let me know what you think about that one. So the next one was day 5. What did we change here? More functional stuff. You can use as bytes and windows for strings. This was kind of new to me. I think what I had done before was turned it into a vector of characters, and then I was able to do the windows on it. But you can actually do line as bytes. Again, this won't work for non-ASCII code, but we're using ASCII here. But that allows you to kind of like skip the step of having to collect all the characters. In the real world, this is probably not a big deal. But if you're interested in performance, this is an interesting way, I think, to do that. Excuse me, is you can say, oh, I'm going to use line as bytes, and then build my windows from there. So not too tough. And I think I do the same thing up here with P1. Oh no, I don't. It's just this one. Remember, so this one was, you have a string and you have to figure out like whether the strings were like good or bad, and they had some rules of whether they were good or bad, right? And so you had to pick that out for each of them. P2 had some interesting rules, and we actually got a comment that led me to believe that I could do this in one window. And so that's why you see me doing it this way. And it totally worked, right? The idea was you can check for you scan you do windows of 3 and you scan, look for repeats, and then it was an order of things. Like first you add the last 2 to the have I seen a double, and then if you have, then you know you're good, but then you push the first 2 on the list of have I seen a double, and that seems to find the double that you're looking for pretty well. And so you can see I turned that code that was maybe like, I don't know, 20-30 lines into just like 6 or 7 lines of code where I say, give me the bytes, break it up into windows of 3. Now I'm going to scan with 2 false values, and I'm going to just keep spitting out whether I found a pair and whether I found a repeat. And if I found both of those, or if there's any where those are both found, then I can stop and return true. So anyway, I thought, again, this is kind of a cool use of scan, but also using as bytes for window 3. I think this is something that I'll probably try and use more often. Again, it won't work in like non-ASCII code, but I believe that all the stuff we do is ASCII code, so hopefully that won't be a big deal. So those were the changes for day 5. Again, great comments, and thanks for bringing that stuff up. So the next was day 7. What did we do here? Oh, this is another one where I removed nom, and I think I'm feeling much I'm feeling a lot like nom probably doesn't work for most of the cases. Maybe in future years that will change, but the way the inputs are set up, it's like very easy to parse them. And so this is one where I actually removed nom, and you can see that you can compare and contrast. But like right here, for example, where I'm parsing the operands, if you remember, this one had some instructions you had to parse, and each of them had like different, and the operands could either be an actual value or a stored variable. And you can see here, like here's where I have the operand part. It used to be I had to do some logic in nom to do that, but instead I can just say, oh, see if I can parse it as an integer, and if I can, use that. Otherwise, assume it's a variable. Much cleaner. And then parsing the instructions where you'd normally think nom would be good because you can say here's what a set and or here's what the different instructions should look like, and then you can, sorry, is it a little loud? I'm going to try and turn it down a little bit. Anyway, you can see there's a bunch of different instructions. They all have different operands, those type of things. And I think nom might be good for, in this case, maybe if I was more adept at nom, but it felt like a lot of code. And so I was looking for other solutions, and it turns out, again, this is a lot. Thank you for the comments. Match statements are actually extremely powerful. And so this felt like magic to me when I learned about this. You can actually, so if I parse a string and I just split it by white space, now I have like an array of characters, right? Or in this case, a vec of characters. I can actually just match on the slice of parts, and it will do the work of figuring this out for me. And again, it feels like magic. So I can just say, hey, does the slice look like this? Or does the slice look like this? Or does the slice look like this? And Rust does the work for me to figure that out. And that feels really powerful. If you look at the previous code, each of these were much more complex from like line wise and like grokking wise in my mind. But the ability to match on slices, I think, is really powerful. And this is really cool. At first I was like, can you even do this? Because some of them are of different sizes, right? These ops have like, 2 different operands and a value, like an output, and then obviously the operation, whereas the not just has a couple, right? And the set just has a couple. So they're like actually different sizes. Like this set right here only has 3, right? But the power of match allows you to do this, right? So anyway, I think that's something that I could definitely improve on and keep working on. And I'll look for ways to like tweak and be better at that, I think, as I'm doing my future days, right? Is like, can I use match to do some of these powerful operations for me? Anyway, you can see like just in like, as opposed to, I think the other one, had 40, 50 lines of code, I can do it in 15 or 20 lines of code. It feels much better, at least in my mind. So again, that's the power of match. So thank you all for your comments and thoughts about, using match and stuff like that. Always good. Where are we next? Day 10. What did we do here? Oh, while let sum. So this was something I did. I did find a functional method to do this, but it turned out to be slower. You can see here. Okay, so what are you trying to do here? Is you're trying to find. You're doing the look and say, right? So like 1 1 becomes 2 1s, and then 2 1 becomes 1 2 1 1. I don't know if you remember exactly how it goes, but I found some cool ways to actually do this. So this way, for example, which is commented out, so maybe hard to see, sorry. You can actually do an iter, and then itertools has dedupe with count. So it will collect all the values that are the same and then give you the value and the count of that value. And so you can actually flat map it and collect it. So this is, this solves part 1, just these like few lines, which I think is really cool and powerful. It was actually like 10 times as slow though. And my guess is because it has to like, the dedupe part has to like create new vectors and stuff like that. Whereas this solution, if I do like while let sum and I get the characters, and then I do, while, so this method is like I use while let sum a couple places, and I think it helped out with the solution. The idea is I just keep peeking and moving the character until I've like found all of the same, and then I push the count and the C and then update it. So what this part is, why is this faster? I suspect, again, because this dedupe with count has to like collect them and then give you the count and the value that it did. Whereas this one, I can just like kind of like peek and next through it, kind of like just so I don't have to worry about collecting them anywhere or anything like that. Although presumably you wouldn't have to the dedupe with count. Maybe you don't have to. So I actually don't know why it was. I think you should be able to do this just by tracking the current character and how many times you've seen it, but it turned out to be slower. And this way much faster. So I had a lot of fun kind of working with this while let sum. I think it was in the comments too, like these let sums are actually really powerful. So keep those in mind, right? It's very easy for you to like find breakpoints and find, you know, how far you can go or when you should stop by using while let sum, and then something like a peek, for example, where you can say like, maybe I don't want to pull off the next character, but can I see what the next character is to allow me to decide what to do. So that was day 10, I think. The next one, day 11. Let's see here. What did I change? Oh, this one doesn't have a lot of changes. I did realize though, this one was a password one, I think, right? Yeah, like the idea is you're trying to do find the next password based on some constraints. And for this one, I realized I can just reuse the password. That actually sped it up quite a bit, right? So that's something to think about, is thinking about your data structures, is like how can I reuse the memory I've already allocated? That will save you some time. Has two pairs changes. Oh, this is one where dedupe with count was actually useful. This one was trying to help you find, you know, does it have two matching pairs that are the same? And this dedupe with count and then filter actually helped me find those groups, right? It's not two pairs that are the same. It was like, can you find an AA and a BB, or an AA and then somewhere later another AA or a CC? And so this dedupe with count was actually really cool because this will actually tell you how many there are. And so I would filter them and say, hey, only give me the dedupes where the count is greater than or equal to 2. And then I just take that value and divide it by 2. And that gives me the result, right? Because there's an idea is like, if there's 3, like imagine there's 3 A's in a row, that should only count once. It's not the first 2 and then the second 2. So, but if there's 4 A's in a row, then I can use like these 2 count as 1 and then these 2 count as 1, if that makes sense. And so I can literally just dedupe with count, filter, map that, and then sum those up and see if I get more than 2 or more. And that helped me solve that problem. So again, this is kind of, you know, if you're using iter tools, this is a cool thing. It might be fun to try and re-implement some of these iter tools just so you feel like, oh, I know how to do it. And so you don't feel bad as like reusing someone else's code, if that makes sense. So I think that was it for day 11. So let's move on to day 13. Oh, I found a couple cool things with day 13. You'll notice I'm also using FX hash map. This is something just, I think if you're solving programming problems, I've talked about this in the past. It's a faster hash map. And the reason it's faster is because the normal Rust hash map, its hashing algorithm is considered cryptographically secure, meaning it's like resistant to certain attacks, whereas this one is not. So you probably wouldn't ever use this in real life, depending on what you're doing. But for our puzzle solving, it's fine to use this, and it gives you a healthy speed up. But day 13, this one had to do with what was it? Oh, you had a round table of people, and you're trying to find the best placement, the best arrangement of the people. Yeah, so my calculate happiness function, I think there were a couple solutions to this. There was one comment that had mentioned using like zip, like offset by 1, because if you zip offset by 1, then you like lockstep go through them all eventually. I also found this function from itertools called circular tuple windows, which has the same effect. The nice thing about itertools is for most things, like you can say, give me a window tuple, and then it gives you like the two things as opposed to a vector that you have to like work with. And so that can be fun. And so I use the circular tuple window, and that gave me the left and right of both sides, and then I was just able to calculate the happiness on both sides, and that worked. You can see you had to do some funkiness, right? My arrangement now looks a little funky because of doing it that way, I think. So anyway, the circular tuple window is kind of a cool way. And I also switched from I think I told you I have my own permutation combinations. itertools does it too, so I just thought I'd use itertools as I was cleaning things up. I mean, I think mine works just as fast, so, but the permutations allows it to work as well. So I think that was it for day 13. Anyway, there's just really quickly though, I think it's worthwhile to look and understand the libraries that are there that are commonly used. If you have something like circular windows or permutations, definitely look into using those. Day 15. This was the ingredients one where you're trying to find like the best set of ingredients. And this was a great one for implementing add and sum and those type of things. And I just didn't see that. So thank you to the comments for mentioning that, right? The idea is, I don't know if you remember, but you have like a list of ingredients that you can use, and what kind of scores they have based on these things, right? Like how durable they are, what flavor they give, what texture, and how many calories. And then you're supposed to like maximize like those values and like find, I think that in part 2 you have to find the exact number of calories. I was doing a lot of the logic manually, but if you implement add, you can just start using the plus sign. And the same thing if you implement sum, you can take an iterator and create a sum of them. And in this case, the sum is really easy because I've already implemented add. I can just do iter fold, and that will return the sum. So what you see then in places, let me find some places. Is it like right here, I think, where normally I'd have to, no, it's in the calc scores part, where normally this part right here, normally I'd have to like add them up. There was like 50 lines of, not 50, but there was a lot of lines of code here where I would like add the values up and then sum them myself. But now I can just use this iter and then change my original score and then sum them all up, chain my original score to get like the total score. So that was a cool idea. You say to yourself, oh, if I can do this, suddenly the other code looks a lot cleaner, right? And I think that's the case, right? Is if you look at this and like you look at this stuff down right here, once you've implemented those things, it makes this look much more readable, right? So that, I think that was a cool use of that stuff. Let's see, day 18. These match things. This was the Conway's Game of Life, right? And in this, when this like match, it was pointed out in the comments that you can actually match on both of these. And in hindsight, that makes sense and is totally obvious, but sometimes you need someone looking over your shoulder. So thanks for that. And yeah, so you can see, I can say like if there's a hash and there's 2 or 3 neighbors, then it's a hash. If it's a dot and there's 3 neighbors, then it's also a hash. Otherwise, I can do this other match to see if I turn them on or off. And this one I also simplified too, I think, with, I don't remember if it was comments or not, but if I pass the corners, if I'm going to turn it off, like this is like the quote unquote turn off that position. In part 2, I always wanted to have the corners turned on, so I can just pass the corner and I can say, hey, if I'm going to turn it off, check first to see if I'm one of the corners, and if I am, turn it on instead, like keep it on. And that simplifies my part 2 code right here. It used to be I had like, before I counted them, and in each iteration I like turned the corners back on, but instead I can like pass the corners here, and then I can do that within the step function, and that simplified it a lot. So again, I think this one was showing you the power of match arms, and matching in general is it kind of feels like if you can do it, or if you can think it, Rust can probably match on it, which is, I mean, it's a little crazy to say, but it actually works. Day 20. This one I think was relatively slow, but it was, I still got like a good solution to it. Like I was able to solve the problem, like relatively efficiency. But there was a note about kind of using a Sieve of Erasmus. Maybe I can open up that link, show it to you. Maybe. Here we go. So this Sieve of Eratosthenes, the idea being like, well, the way the Sieve works originally was for prime numbers, and the way it worked was create a table of all the numbers and then mark all the things that are divisible by 2 off, then mark all the things that are divisible by 3 off, then mark all the things that are divisible by 5 off. And eventually you start getting to, you know, numbers that must be prime, if that makes sense, because they haven't been touched by any of the numbers before them. And this idea of updating a table turns out to be way faster for this case. So if you remember what the puzzle did, was it was asking you about, or it was saying elves delivered presents in steps. So the first elf would deliver it to every house, the second house every other, and the third elf every third house. And so what you can do is say, and then it was going to tell you, like, and the question was, at what point, at what house have you delivered at least the size of your input? And so you can kind of do, you know, I picked a number here, 1 million, and that felt like it was enough to ensure that I would get my input. You could probably do some math to figure out like how far, based on your input, how far you think you need to go, because you can imagine like on the millionth step, some number of elves before you would have delivered to the 1 millionth one, and you know you won't ever have to go above that, if that makes sense. But anyway, what I do instead, what I used to be doing is like checking each one. I would do like a divisor thing where I'd say like, okay, at house 10, I know I can be visited by 1 and 2 and 5 because those are the divisors of 10, and then obviously 10 as well. This works the opposite way. So instead of thinking about each house, you think about each elf. So you say, for each of the elves, have them deliver the houses to each of the houses and update my vector. And then I can just say, if I ever get to a house for this current elf that's greater than my input, then I'm done. And for part 2, where the only thing that changes there is I was only supposed to, each elf only delivers 50 times, right? So the 202nd house would not get a package from the second elf, because the second elf stops after 100 or whatever, right? Anyway, this made it super fast. So this is one of those things to think about when you're problem solving that sometimes I struggle with. I feel like I'm better in some areas than others. This is one that didn't occur to me, and so thanks for the comments to that. But it is something to think about. Sometimes you got to flip the problem on its head. Is you say, okay, well, instead of thinking about the problem from each house, think about the problem from each elf, and then that simplifies the problem. So anyway, just something to keep in your toolkit, in your mind, where it might be useful. Okay, day 23. Let's see, what did we do here? Oh, this is another one where this is one where we are implementing kind of like a little computer with some instructions, and implementing index and index mute. This was a really cool idea from a comment, right? As opposed to I had a lot of code where I was like checking, is it register A or B, and then picking the thing. If I implement index and index mute, it's now really easy just to say, you can see it right here. I can just say, hey, change based on the register, get me the register and update it to the current register value divided by 2 if I'm halving. So this R value is the register. And so that greatly simplifies that code, right? So that's totally a cool way to do this. So you need to implement, in this case, you need to implement index and index mute because you're getting the value, but you're also setting the value, right, to like half or triple or incrementing it. Anyway, so that saved a lot of space. I also moved the evaluate into a new data structure for a machine. And the reason why that made it much simpler, I don't know if in the previous code, I had done some weird stuff where I had to like pass a bunch of mutes and pointers and move them around and had these helper functions that allow me to change them. By doing it here, the evaluate looks a lot better because I can just interact with self. So I increment the program counter, I increment the registers as I need to, and it feels a lot cleaner to do it this way. So I feel like this solution, at least for day 23, is much cleaner than my original solution, if that makes sense. Day 24. Okay, this is the one we'll probably spend the most time on. My solution was super slow, and it turns out my solution was super slow because I was like creating iterators, or I was creating like vectors with every check. And so like you imagine the check of like 500,000, creating the vectors and checking them, and then creating new vectors and checking them, creating new vectors and checking them, doing that like 500,000 times was like really slow. So I actually could do it faster, like sub 1 second, if I did this part right here minus this line. So if I delete this line, this is my part 1 solution, my original part 1 solution, but updated to not do the extra checking, or sorry, not to do like the vector creation and counting. And this actually runs really fast, right? Like it's like 10 milliseconds. I don't remember the exact number. Super slow. What it doesn't solve, though, is the general case. And that's what this other filter is. So if you remember what we're trying to do in this problem is Santa's sleigh is off kilter. You want to, or how did I say this? Santa's sleigh is broken up into groups, 3 groups, and you need to find like the perfect the perfect weights of presents to put in the 3 different groups. And so my initial thinking was, oh, well, I'm only worried about the first group. So I just iterate through a bunch of combinations and find where that first group fits. And that actually solves the problem. So again, if you remove this part, at least for my input, that solves the problem. Is like, I only care about the first part. Can I find the first part? Can I find that first group that is the smallest and, equally distributed and things like that, fits all the rules? What I didn't consider though was the case where like after that though, do the rest of the packages split evenly? So in the generalized case, you actually have to answer this question. So you say, okay, am I the smallest group that I can put in part 1? That's this filter. But but that other part, you had to say, okay, well, can I partition the remaining filters? And that's actually a harder problem. That is called a K partition problem. You'll see it called a 2 partition problem or a 3 partition problem. And this can be really slow if you just like try all the iterations, because there's a lot of them that you had to pick from, right? Especially when the number of, in our case, packages is very large. But this is a known algorithm, so I did some research and found like the known algorithm. I don't know if you remember too, I was looking at trying to find, I found some other solutions that were faster, and I wasn't sure how they were faster. They essentially do this can partition remaining function. And so I'll explain what that is and how it works. But otherwise, the algorithm itself doesn't actually change once you do that. It does help to sort, so try the largest one first, because what we're going to do is a depth first search of the solution tree. And obviously, you know, the bigger ones have a higher impact of the equalness of the weight, if that makes sense. And so sorting them helps. So this line changed, but otherwise the only thing that changed in my original solution is this part here. Obviously I made it faster by using this filter and this combinations and filters. But there you go. So what is this? How does this can partition remaining work? There's known solutions to this, and so I'll show you kind of briefly. You'll probably have to read the code to understand a bit more of how it works, but the idea behind a generalized algorithm, especially for like you know, can partition K items, like partition K partitions, can be really hard to solve efficiently. In fact, I think it's like a known NP hard problem. The idea, though, is that there's possible ways to do it faster, quote unquote faster, if you do it if K is 2 or 3. In our case, it's actually not faster because of the size of the input. Anyway, we'll talk about it in a minute. The generalized solution, and the one you should probably use most of the time, is just called DFS with backtracking. And this is like a dynamic programming problem. And I don't know why it didn't occur to me to use this when we were doing it, but this is a great way to do this, is dynamic programming. Basically, essentially what you're doing is you're trying to fit solutions. And we've done this in previous days. Like the idea is you're like, well, what if I take this weight and put it in the remaining slot? Can I solve the subset of the problem where I have to fill this side and this side with what's left? And you basically do that until you find a good solution. The reason they call it backtracking or pruning, sometimes they call it also, pruning is I think this does pruning as well, is the idea is if you ever imagine like the whole solution tree is like this big tree that branches out like this. If you find like a subsection of it, like right here, where you know this part of the solution never works, you can like eliminate that whole tree. And if you ever see it again, you can just eliminate chunks of the tree. And it turns out to really reduce it. So I'll talk about can partition K really quick. The idea is you give it the weights that you want, or the numbers, and you give it like a little map of like which ones have I used. And then you give it like how much remaining weight is there and what is my target. And what it does is it basically just does some high level checks. It says, oh, am I done? Can I solve it? That's what these two things check for. They basically say, can I still solve it with what I have, right? So you say, oh, what is the total remaining? And can I get there from this? And if I can't, then I know I can't solve it. If k is 1 and I can solve it with that, then I know I'm done. So I return true, right? So k is 0, I can return true. If k is 1 and I have the exact weight left over that I need, then I've also solved it. If k is greater than the package length, then I also can't solve it. I should say this comes from, maybe I can open the link and show you. This comes from this thing right here, the multi-way number partitioning. So there's like some known algorithms we'll talk about to solve this, but it essentially says the one that solves it in the general case is the dynamic programming solution, which is what we're doing. We're doing the dynamic programming solution. So I'll provide all the links, by the way. But basically what you do is you say, can I partition, these packages of size of target, of this target from these number of partitions, right? So k is the number of partitions. So if I've met all the if I haven't met all these criterias, I now know I can do a DFS search for like the next group to try. And what the DFS does is that basically this is just recursion, where I say, hey, have I found my target weight? And if I have, try and do can partition k again, but for one smaller size, right? So if I found a chunk of weights or a group of weights that works, I'm going to remove those weights and I'm just going to say, can I partition what's left with k minus 1 groups? And so again, because we're only partitioning twice, once I found one group that meets it, obviously this can partition is like the last group and then it would work. But if in part 2 we start with k equals 3, so there's like 3 boxes. So the idea is I try and find this one group, and then if that works, I'm going to see if I can partition the rest of these. And if I can, I'll recursively go down and try all those, and then eventually it works. Obviously, if I've gone over my target, then I can't, the DFS failed. Otherwise, I just start from my beginning position to my weights, and then for each of those weights, I do some checking to make sure I'm not going over and that the weight wouldn't cause issues. But otherwise, I say, okay, I'm going to use this weight in my group, and then I'm going to DFS again and see if I can solve it. And I just go through that. So what that's eventually going to do is, maybe the way to think this, the DFS is like the backtracking part of it, or like the filling and backtracking. The DFS is going to try and create a group of them, and anytime it creates a successful group, it's going to try and partition the rest of them. And so I could probably rename these better, but the DFS part is like the try and create a group. And once I've created a group, call partition on the rest of the things. The thing that makes this fast, and the reason like my previous solutions were slower, is why the previous solutions were slower is I was using a vector and I was like filling up and reducing and filling up and reducing the vector, going back and forth. And that made it really slow. The key here is, or the thing that helped me the most, was to have this used thing, right? Is what is the list of things that are already used, the weights that are already being used. And once all of those have been used, and so that allows me to do simple things like, ignore the ones that are used, or up here, when I'm counting what's left, ignore the used ones, those type of things. So that'll help a lot. Anyway, you're welcome to read through this. It was another thing. I think this is like an area where I'm probably still weak on, is remembering like these, sometimes, I don't know, sometimes you read problems and you want to try and fit it into something about. And so this is another place where it's good to know, if I want to solve a k partition problem, here's how I can solve it. Now I'm going to dive just a little bit deeper, so bear with me. In this partition problem, oops, where did that go? Did I get rid of it? There were some algorithms. I did get rid of it, huh? Okay. There were some algorithms that talked about like faster ways to do this. And this is a pseudo polynomial time number partitioning. And I won't go over all the details. This is an algorithm that can do it in, where is the number? kn time. In our case, we're doing a k-way partition. So a k partition, meaning this, let me clarify. This algorithm is designed to work on a two-way partition, meaning you're just splitting them in half. But you can because of the way the algorithm is designed, you can technically do a three-way or a four-way or as many as you want. It just makes the loop longer and bigger. I'll show you in a second what it looks like. You do additional loops to solve the algorithm for as many k's values that there are. But anyway, it can solve it in kn time, but it requires a lot of memory. It takes n times k minus 1 m k minus 1 time or memory to do this. And notice it says that can make that impractical for k equal 3 unless the points are very small numbers. And why does it say that? What you're actually doing in the algorithm, if you're looking at it, you're basically creating an entire table of solutions, and as you're looping through, you're like adding weights to those solutions to see if they're possible. And then eventually you have like a list of a list of partitions. In our case, one is like a group of 3 and then another is a group of 2, and then you just ask the question, can I from this giant list, can I find the one that splits them in half? It's a really cool algorithm, and it works well for 2, assuming you have a bunch of memory. It works okay for 3, assuming the size is small, and it turns out it has to be very small. For our 200, I think we had 29 boxes, and our weight was 1,500. The number of iterations you have to do is like 3 million, 4 million. And so it actually makes it slower for the 3-way, substantially slower. And it's still slower for the 2-way because of all the memory allocation. There might be ways to speed it up. Did I speed it up? Let me go look. Let's see if we sped it up. Anyway, if you want to try it out and see, you can uncomment this code and comment this part out, and you can have it match I added this match and say, hey, if I need to split by 2, I call can partition 2. If I need to split by 3, I call can partition 3. And so these are the two things. So how does it work? Here's the code right here. Basically, I create a giant vector and say, oh, these ones don't work for the can partition 2. And then what I'm doing is I'm looping through and I'm saying, hey, have I used this value yet in the left side or the right side? And I add those weights to the value. Notice this is like target plus 1, right? So in our case, it's like, what was it? 512 per each side, somewhere around there, 500. So I'm creating like 1,000 vector array, which is not too bad, but I have to loop through all the value, loop from A to the target, which is 512, and say, can I put that in there? And if I can, I update that DP value with the target. And so this actually, you can see, but once you've like filled out the array, you can then just ask the question, is can I make a sum of target, in this case, which is 512 or 20 or whatever? I don't remember exactly what it was. Can partition 3-way work similar, except now you have 2 targets, right? You want to think about it as what you're trying to group is k minus 1 groupings, and so now I have to do 2 of them, which like effectively like doubles the size, but it also doubles the loops, right? So this can partition 3 takes like 4 million iterations. Like if you were to put like a little counter right here, it would take 4 million iterations, 4 million like ticks of this loop to to solve the problem. But it's a lot of weird math. It works essentially the same way, where you're like, you have a bunch of weights, and you're only turning the weights on if the value of like the value can be put into that weight and broken up. But you eventually turn them on, right? So you can see here's where you like turn them on for subset 1, turn them on for subset 2, and then you can just ask, can I turn on for subset 1 and subset 2? Meaning you've like broken them up. Can I turn them on for those things? So you're using the target twice essentially here, whereas you use the target once. The cool thing about this is it actually will tell you once you're done how you can break them up. So you can ask yourself, can I break it up into 300 and 600? Like if the total was 900, you can say, can I break it up into 300 and 600? And it will actually tell you that, as far as I can tell. But this is quote unquote faster from like an big O notation, but in reality, it's actually not, because this can partition K, this branching is just super fast. So again, and I think these K equals 2 and 3 ones, these can partitions, probably aren't helpful unless you know enough about when you'd use these algorithms. But this one is like generally usable. And like the only reason you'd have to say, oh, do I know how to use these, is for like a very specific case where the input is set up in such a way that this can partition K just wouldn't work. So what I guess this is all to say, I've spent 20 minutes talking about this. Again, probably think about the problems that you're trying to solve and how algorithms might fit into them. Can you like generalize the problem to an algorithm you know about? And in this case, the thing that I was missing was, oh yeah, the can part, can I like split up the remaining group? I don't, let me just clarify really quick. I don't think there's an easy way for you to find the first group, because the first group had some very specific rules. You wanted to minimize the size, and you wanted to maximize the quantum entanglement value. Was that it? Or was it minimize them as well? I think it was maybe minimize both. But that makes the DFS really hard to do, because you won't know if the DFS for that solution is like down this side of the tree until you've tried it, which means you basically have to try the whole DFS tree. You have to like, maybe an easier way to say it is that you can't really do pruning, because you don't know if a later value would put you in a lower thing. At least I couldn't find a way to do it. Maybe if you find a way to do it, I would be interested in seeing it. So I actually think my initial solution was the correct one. Is like, for the first package, you just have to try all the combinations, and then filter by the ones that meet the criteria, and then ask yourself, can I partition the remaining? And that's where you would say to yourselves, oh, this is a partition K problem, I should use this algorithm. That's the point I was trying to get to. The actual problem itself is not, how do I say this? A subset of the problem is a partition K problem. And so we should understand how to do this partition K thing. And this also works in other places. I don't know, that I've seen other problems on LeetCode where I've used this before. That's why I was kind of like oh duh, why didn't I do that? Because I have seen LeetCode problems that want you to implement this. And so understanding how to do this can partition K is probably worthwhile. And I think actually if you created an algorithm for it, you could probably use it in any problem, because the can partition K problem is just saying, can you do this, yes or no? So you probably reuse that over and over again. Anything else I want to say about that? Yeah, again, so it's this like, and this is, sometimes I'm really good at this, sometimes I'm bad. I think it's the knowledge of, do you know the algorithm? Have you used it enough that you can say, given this blob of text, can I distill it down to this is the algorithm to use? Sometimes that's easy, sometimes that's hard. Learning how to do that, I think, is helpful. But part of the thing is you just have to know the algorithms as well. And I've used this before, not familiar with it. I couldn't write it from memory, so I used Wikipedia, I think, to help me with this. Um, it had some pseudocode, and then I used I built this from the pseudocode. Anyway, but I think this is also a problem where it's helpful to think about upper and lower bounds, which I believe I talked about in the video. Always check your bounds, right? We were able to like greatly simplify like the solution space that we had to check by doing like creating sane boundaries based on the inputs. And so I definitely think that thing is worth doing. So anyway, I'd love your input on part 24. I think I'm probably releasing this as that part 24 is coming out, but I'd love to hear your input, because I definitely think this is something I could improve on and get better at. So let me know what you think. Okay, the last one, day 25. If you remember, this one was like a what even was the problem? Oh, it was you were trying to you're trying to get the next code based on your current value, and like the code was done in diagonals. And in my original code, I think I like basically stepped through it and said like, okay, here's the first one, and then I need to, you know, step down and go up, and then I go back to the beginning row and go back up. You're creating these like diagonals along the chain. I almost positive I said there's probably a math way to do this. I just don't know what it was. And the answer is there is a math way for both of them, right? You can find the total number of steps that you need to take to get to there via math, as well as you can solve the actual problem with math knowing the steps. And so I won't go too long into this. I'm actually like, math is probably where I'm often weakest. Like when it feels like it's a quote unquote math problem, I feel like I have to do searching. But it did it's another reminder of like, oh, put modular exponentiation in your toolkit of, when I see a problem like this will solve it. But let's first talk about like, the first problem is you're going in rows and columns. Maybe I can find the day and show you. It looked like this. You're trying to solve the codes in the diagonals. And so the question was, if you're on the 18th code, or you want to find the 18th code, how do I find, you know, how do I know how many steps that is? Because you really only have a row and a column, right? If you're right here, obviously we know it's 18, but how do we know it's 18 if we were given like a row and a column, if that makes sense? And it turns out the way to do that is find this diagonal before it. And I think I had mentioned this in the video. You find this diagonal before it, and then you just add what's left in this diagonal right here. And this, if you look, is a triangle. It forms a triangle, the triangular numbers. And the way to solve that is this formula right here. N times n plus 1 over 2 gives you the sum of all the previous diagonals. Then you just add the whatever's left, right? So I tried to explain it here in the comments. So I know the last full diagonal is row plus column divided by 2. So imagine I want to find this one. The last one is row times column minus 2. So 7, 5, 1, 2, 3, 4, 5. So there's 5 on that column, right? Does that make sense? And then I can just plug that into this equation here, n times n plus 1 over 2. That gives me the sum of the previous diagonals, this triangular section right here. Then I just need to do what's left, which is this plus columns minus 1, right? So because I'm going to go up the columns, right? Like if you think about what's left here is I'm stepping up the columns to where I'm at. So I just do that. Sum plus column minus 1. I think I did that the wrong way. These are the columns, right? So like 1, 2, and 3 right here. I do minus 1 because they're 1 base as opposed to 0 base, I think. Anyway, that's how you figure out how many steps you need to take. But then the question is like what it actually asks you to do is where the math comes in. And this is just where I think if you know the math, it becomes easy. If you don't, maybe you try it by hand and then it's slow. And so you go look for a math solution. This is one where it should stand out. Oh, there's a math solution, like I said. And probably in the video, I actually don't feel bad about doing this. I don't think there's a problem with like Googling this and saying like, hey, how would I solve this problem? Or maybe asking AI, is there a math way to solve this problem? Probably not a bad idea if you're not familiar with the math. But then once you know it, it might help you, right? That's the hope. And why is this help? Why is it a math problem? And why did I come to modular exponentiation? Well, I was looking for, if you notice it says, you start with this value and then you multiply, divide, and remainder. Wait. No, it's right here. The first code is this. After that, each code is generated by multiplying, then keeping the remainder of dividing by this. So the remainder. When I was looking up, hey, how do I do this? It turns out the answer is modular exponentiation. So I'll show you the link that kind of helped me solve it, what I found. And you can see right here, like this is essentially what we're doing, right? We want to compute some hard thing multiple times. And it turns out there's an easy way to do this. And here's the algorithm. The algorithm is actually absurdly easy, right? You set some initial values and then you just loop incrementing and calculating the modulus, and you do it until you've handled all the exponents. And it's called modular exponentiation because the idea is you're raising something to the exponent mod some value. So the idea is you can, for each of the values in the exponent, which is the number of steps we take, which is this thing, the number of times you're like doing that thing. The modulus kind of keeps it bounded. And so you're able to kind of like do this in a loop based on the number of steps that you have to take. And it turns out to be much simple. Do I have that right? The base, the exponent, and the modulus. Yeah, I think I have that right. Yeah, because then when I'm done, I've done the modular exponentiation, and I can just times that modulus this, if that makes sense. So I was able to use U64. I've seen when I went looking for other people's code, I've seen them use U128s because these can get really big. But anyway, the thing itself is pretty simple, right? And again, this is something that I'm just not familiar with. This one I probably should have known, or I could have figured out because I've worked with diagonal numbers before. I just didn't know this algorithm. But if I said to myself, oh, this looks like a triangular number plus something, I could probably looked up triangular number and solved it. This I have used before. We've had to use modular exponentiation to solve a problem before. But again, like I said, I think I've forgotten more things than I've remembered, if that makes any sense at all. And so I did have to kind of like do some Googling to find this. My original solution actually worked. It took like 100 milliseconds or whatever to solve it. But this way is substantially faster because what you're doing at each step is like very small, right? And you can just do it a math way. So it takes like microseconds or whatever as opposed to milliseconds to solve it. So again, this is another day like day 24 where it's like it's good to have a bunch of algorithms in your toolkit while you're solving problems, because if you can hone in on the correct algorithm based on the problem and the inputs relatively quickly, that will get you to your solution fast. If you're just trying to solve it for fun, then I don't think, if you don't know the answer, like I didn't, clearly I didn't have the right answer for these last 2 days, even though I solved them. um and by right, I mean like the algorithm to solve them efficiently. um if you're just having fun, I think it's fine to look them up, Google them, maybe ask AI to help you. However it is that you learn and grow, I think is great. um and so, uh if you're doing it competitively, though, you probably need this whole, I have a bunch of these in my toolkit and I've memorized all these ways to do it, and I know how to solve them by hand quickly, or I have like a pre-made library that I can solve all of these. And like I've said, modular exponentiation is one that I've seen before. So you should probably just have that in your toolkit if you're trying to do competitive programming. Okay, so that's all of them. That wraps up 2015. Again, I think it was a great year. The first few days, the first, I don't know, 10 or 15 days, probably half of it I felt like was pretty easy to solve. But maybe that's just because I've been solving problems for a couple years. Maybe they were hard for you if you're new, or you're trying it with a new language and you have to like research the standard library or the commonly used libraries in your language. I can see those things being harder, taking some more time. Or if you're trying a different paradigm, right? Rust is still largely um akin to like writing in C or whatever. But if you were moving over to like Haskell or something like that, you might take you some time to solve those problems. um but there were a few days that I definitely felt like I learned, and I think that was the important part of it, is can we learn from this stuff? I definitely felt like that happened. So for me, it feels like it's worth it. I felt like I got some reps in, improved my Rust, improved using things like matching and stuff like that. The hope is that, especially with this recap and going back and fixing the days, those things will be better ingrained in my mind, so that when I see a problem, I can say, oh, this is, dynamic programming with backtracking and pruning, or this is modular exponentiation, or this is a graph problem. I tend to do better at the problems that are like graph problems, just I think probably because of my familiarity with graphing, or with graph theory and stuff like that. So anyway, I'd love to know how you did overall, what you thought about your 2015. It is the first year. There's definitely, I know there's days coming up, because I've done them before, where really hard problems and not easily solvable. We'll see how those go. I'm gonna keep doing this. I'm having a lot of fun doing it. um Hopefully you have fun watching. And let me know how I can improve. Let me know how you did things differently. All that stuff definitely helps me, and hopefully it helps you too. So with that, thanks everybody, and we'll talk to you next time. Bye everybody.